Hi all. We were discussing about photosensitization in the previous class. So it's a technique for the deactivation of the energy from a molecule which is already excited. There are few more techniques as we have already discussed that happens to be a method for molecules for the de-excitation of electrons from the higher orbit to the higher energy level to the lower energy level. One is quenching of fluorescence. There is an equation related to this quenching of fluorescence that is called the Stern-Boermer equation. What is quenching means? If the excited molecules are deactivated and the fluorescence stops, the phenomenon is called quenching. There are two types of quenching. One is when the activated molecules undergo a change from a singlet excited state to a triplet excited state. This is called internal quenching. The molecule is getting de-excited, but no radiation will be emitted. So internal quenching means singlet state to triplet excited state. When the activated molecules collide with another molecule so that the energy could be transferred to another molecule, that is called quenching, but external quenching, which are externally added species and transfer their energy to those molecules, is called external quenching. When a molecule is absorbing energy, we say the molecule has got activated, so we represent it by using star, A star. And the excited molecules can get de-excited in many ways. One of the ways is fluorescence, where the excited molecule emit radiation in the form of fluorescence. So A star gives A plus h nu, K1 is the rate constant. And another way is the activated molecule A could deactivate by internal quenching, singlet state to triplet state, or it could be external quenching, colliding with another molecule and transferring the energy to another molecule. So A star plus Q gives A plus Q. Here the A is deactivated. So if you take the intensity of the light absorbed, that will be the combination of all this process. So IA, intensity of the radiation absorbed, is equal to K1 into A star plus K2 into A star plus K3 into A star into Q. Suppose if the IF represents the intensity of fluorescence, you can find out the efficiency, that is phi F. It's actually phi or phi Q is equal to IF divided by IA, that is K1 into A star divided by K1 into A star plus K2 into A star plus K3 into A star into Q. That could be simplified as K1 divided by K1 plus K2 plus K3 into Q. This equation is what we call Stern-Boermer equation, which deals with the kinetics of photophysical intermolecular deactivation process. Another important topic from this chapter is quantum yield or quantum efficiency. We came to a definition of quantum efficiency by taking the help of EINSTEIN'S law, that is Einstein's Stark law, we have already learned. So what is quantum efficiency if you ask? It is the number of molecules reacting in a given time divided by number of quantas of light absorbed in the same time. This is theoretical. Experimentally, you can say that it's the rate of the chemical reaction divided by quanta absorbed per second. It expresses, the quantum efficiency expresses the efficiency of a photochemical reaction. A photochemical reaction strictly obeys the law of chemical equivalence, that is one molecule can absorb one quanta, then if they strictly follow the law of chemical equivalence, then the phi must be equal to 1. That means the ratio between the reacting molecule and the number of quanta absorbed must be equal to 1:1 ratio. Just like we have seen in many other cases, in case of ideal gases, in case of perfect crystals, in case of ideal solutions, here also very few substances, very few system follows this law of photochemical equivalence, such that a reaction is SO2 plus Cl2 gives SO2 Cl2, and most of them does not follow the law of photochemical equivalence, and phi will not be equal to 1. It will be greater than 1, it will be less than 1, because all the primary process, that is the photoactivation, does not lead to the photochemical reaction or the secondary process or the thermal reaction. For example, if you take the photosynthesis of hydrogen chloride, chlorine reacts with hydrogen to give 2HCl. It's not happening in the dark, means all happens by means of the absorption of quanta. The mechanism of the reaction: first initiation happens, second propagation happens, and the last recombination reaction, that is termination. So it's all about the free radicals. And what happens is, once the reaction is triggered, initiated by the absorption of photon, many reaction will happen. So through the propagation step, many reaction will happen. It's a free radical mechanism. So what happens is, one photon is absorbed and many molecules reacted. So the quantum efficiency will be around million. It's like explosion. If you take another case, that is the photolysis of hydrogen bromide, where hydrogen and bromide dissociate into hydrogen and bromine. Here, what happens is, if you look at the mechanism, you could see that one photon is absorbed and two molecules are reacted. So the quantum efficiency will be given by this equation. It is equal to 2. There is one more example, that is ozone formation in the atmosphere. Here also two molecules absorb. Absorption is the one quanta by two molecules. The quantum yield is 2. Another important reaction highly related to photochemistry is photosynthesis. Photosynthesis is the primary source of energy, all sort of energy utilized by the living beings. Plants use sunlight, carbon dioxide and water to produce carbohydrate with oxygen as byproduct. The overall chemical reaction summarizes the process as carbon dioxide plus 2H2O. It happens in chlorophyll through several steps to give CH2ON. It is nothing but the carbohydrate plus H2O plus O2. And in the case of photosynthesis, the carbohydrate is particularly glucose, C6H12O6. So the reaction could be written like this. This is the basic thing, but if you wanted to relate this photosynthesis with photochemistry, you are supposed to write like this. Light and sunlight energy is getting converted to chemical energy finally by the absorption of light in presence of water will produce oxygen, and along with that there will be the production of chemical energy, adenotransferrin phosphate, NADPH. If you wanted to know more, you need to refer. And this, through the Kelvin cycle, carbon dioxide will be absorbed and there will be the formation of the chemical energy could be accessed by the living beings, that is the carbohydrate. And the first step is called thylakoid reaction. It is happening only in the presence of light. And the second step is called stroma reaction. It need not require the photons, means it happens in the dark. Photosynthesis, where the kitchen is the leaf and the chlorophyll act as the catalyst, absorbing and transferring the photon energy for reduction of carbon dioxide to carbohydrate. This reaction maintains the life on the earth. So in presence of sunlight, carbon dioxide and water react to give carbohydrate. Then another very important question related to your board exam is, how do you determine the quantum efficiency experimentally? We know that the equation for quantum efficiency is number of molecules reacting in a given time and the number of quanta of light absorbed in the same time. So if we get two informations, we can find out the quantum efficiency, we can determine the quantum efficiency. Number one, the number of moles of the substance reacting in a given time. Number two, the number of quanta absorbed in the same time. So in order to determine the number of moles reacted, we can take the help of chemical kinetics of the reactions. The chemical kinetics of the reactions are used to determine the number of moles reacting in a given time. To measure the rate of the reaction, small samples of the reaction mixture are taken at definite intervals of the time and analyzed. In order to determine the rate, we could measure the change in some physical property like refractive index, optical rotation of the reaction mixture. So by the help of kinetics, we can determine the rate of the reaction. That's all important over here as far as the determination of the rate of the reaction is concerned. The rate of the reaction gives the number of moles of the substance reacting per second. Now the important part is determining how many quantas are observed in a unit in that particular time. In order to estimate the intensity of light observed, we need to find out what is the intensity of the incident light and what is the intensity of the light transmitted. That could be found out by this equation, Ia is equal to I naught minus I. And how do you determine the absorbed and transmitted, incident in light, intensity of the incident light and the intensity of the light transmitted? What you have to do, you have to take the empty cell, pass the light, measure the intensity, that is the intensity of incident light, take the sample inside the sample tube, and through that you have to pass the light, then you can find out whatever be the energy is transmitted. So the same cell is used. I naught correspond to the measurement of intensity with empty cell known as blank, and I to the measurement using the cell containing the reaction mixture. So this is what the instrumentation. As a source A, visible light, a high intensity tungsten lamp or quartz halogen lamp or xenon lamp can be used. For obtaining ultraviolet light, you need to use hydrogen or deuterium lamp. The light is first passed through a lens B to get the parallel beam of the light and then through the monochromator, that is C. The monochromator yields a narrow band of light in the desired wavelength. The monochromatic light then passes through the reaction cell, that is D. The light transmitted by the reaction cell reaches to the detector and the detector will detect what is the wavelength of the light. The detector is used for measuring the intensity of the light. The quantitative measurement of the light intensity based on energy conversion or on the chemical reaction is called actinometry. The thermophiles and photoelectric cells are also used as detectors. So the determination of the quantum yield mainly depends on how accurately we get the number of photons absorbed in a unit time. So this detectors are very important. There are three types of detectors. One is actinometer, the other one is photoelectric cell, and the thermophiles. Thermopile. So this is the diagram for thermopile. Thermopile is a device useful for the converting light into heat and then heat into electricity. it has a set of junctions of different metals having blackened surface. This part is that. This black coating is to ensure absorption of all the radiation falling on it, because black will absorb. The energy absorbed increases the temperature of the metal, and the temperature rise will be converted as potential difference, means electricity, and the light intensity is related to the electricity generated by it. So this is what the thermopile does. So light will get converted to heat energy will get converted to electricity. Whereas in photoelectric cell, it is directly measured. Photoelectric cell convert the light energy into electricity. The current generated is directly proportional to light intensity. Photoelectric cell is an evacuated bulb with a photosensitive cathode. Light radiation results in the emission of electrons from the cathode, which get collected at the cathode. Thus the flow of current is caused. Chemical actinometer. This is the most important method. Light intensity could be estimated by quantitative estimation of a substance formed or decomposed by light. So the technique is the photochemical decomposition of K3Fe C2O4 thrice, it is the oxalate of potassium and iron, is widely used chemical method for estimating the intensity of light between the wavelength range of 250 nanometer to 577 nanometer. So this is related to colorimetry. Light within this wavelength range causes K3Fe C2O4 thrice dissolved in sulfuric acid to react as follows. So the reaction is like this: Fe3 plus 2E gives 2 Fe2 plus, and C2O4 2 minus gives 2 CO2 plus 2 electron. And how do we understand the extent of this reaction is the concentration of Fe2 plus that represent the number of quanta absorbed is estimated colorimetrically through the complex formation of 1,10-phenanthroline. This complex has a deep red color. The concentration of the complex is equal to the concentration of the Fe2 plus present before the complexation, and the concentration of the complex is determined depending on the color exhibited by the complex.